Who here has used Salt before? Okay, who here has heard of Salt? Okay, well, at least we're getting unanimous hands on that question nowadays. So most of you have not used Salt before. Okay, so I'm trying to gauge I'm trying to gauge how to dive into this talk, because the talk that I've got prepared has to do with a lot of low-level network functionality and different network modularity capabilities in Salt today and where we're going in the future, which might be a little deep of a subject with respect to Salt for people who have not really done anything with it before. Okay?
I would argue that, I don't know, maybe it's not arguing. I've used similar tools a lot and trying to understand better how Salt works under the covers. So, while I'm not an expert at Salt usage per se, that's why I'm here. So.
Okay, so my approach then will be is that I'll spend about 10 or 15 minutes doing a quick high-level overview of Salt. A quick, here's how you use Salt, here's how Salt goes, and then dive into some of the internals and functionality of how it works, so that hopefully I can present something which is beneficial for those of you who are crazy deep Salt users and those of you who are brand new as well, which is of course an endlessly difficult task, and especially one with respect to Salt, because Salt is really easy to get going and Salt is really easy to set up and learn the basics, but Salt is an incredibly deep rabbit hole. And so, yeah, just find a seat, Kyle. We all see you. It's okay. You don't have to be discreet.
Well, I was trying to duck out of the camera.
Okay. So we'll start with a really quick overview. Now, fundamentally what Salt is, am I in a situation where I don't have dry erase markers again? I should have brought them with me. Everything I've prepared is primarily whiteboarding. Well, we'll see what we can do. If anyone sees a dry erase marker floating around, please throw it at me. All right, but so a quick overview of what Salt is. Salt is fundamentally a remote execution system. And the original development goal of Salt was this idea that I had that the right way to get information about what's going on inside of an infrastructure is to ask the infrastructure, instead of the more classical approach, which is to have a database which is filled with outdated data. And so for many years before I started working on Salt, I worked with a lot of different network techniques to try and accomplish this goal. I did a lot with SSH, I did a lot with raw TCP sockets, did a lot with HTTP to try and figure out the best approach. And I started working on this fundamental problem in college and spent 7 or 8 years trying to figure it out in my spare time until I got to the point where I made Salt. And then I'm still trying to grapple with this idea, which is why in Salt there's multiple ways that the remote execution system can work, because we're constantly trying to find ways to make it faster, more reliable, and more modular and more flexible. So, fundamentally, Salt's pretty straightforward. Now I'm running Arch Linux here, so I've just installed Salt by using a pacman-s salt. It's in the main package repos for Arch. It's in the main package repos for Fedora. We've got a PPA up for Ubuntu. It's imports for FreeBSD. There's Windows installers. It's not hard to install. Okay? We've worked very hard to get it that way. And even if you find that it is difficult to install, we have a shell script that will install it properly for you if you just run it called Bootstrap, or Salt Bootstrap. So once it's up, there's really only two things that you need to do. One is that you start a Salt master. There, yay, it's running. It's easy. And the other one is that you start a Salt minion that knows where its master is. By default, the minion will look for a host named Salt on your DNS network. But since this is an extremely contrived example on a local host system, we'll just do that. Fire up a minion. And then when that minion is fired up, it's connected to the master, which is what this log here says. Salt master has cached the minion's public key. You need to approve the key before we're going to be willing to start talking to this. And there it is, the key for localhost.local domain. It's accepted. It polls every 10 seconds. So by the time I'm done explaining this particular point, it will have connected. And we can start firing commands out on our new minion. Now, one of the principal behaviors or aspects of Salt is this idea of being able to fire on minions in rapid succession, or on many of them, many systems at the same time. Okay? And so this particular test.ping is pretty quick, 1/3 of a second, but it stays at 1/3 of a second as you get more and more and more systems involved. And even when you've got hundreds of systems, it's generally able to get information from all of them in less than a second. And then it comes with a vast library of routines. This test.ping is rather contrived. But we've got things like network.interfaces, which normalizes the network information across multiple platforms. And we've got package management that normalizes package management across many, many platforms. Okay? So using Salt is pretty straightforward. You install a minion, you point it at a master, and then you can run Salt commands. There's nothing else that you need to do. And it's been engineered to be very, very easy and very quick to set up. Now that we've got the ability to execute these commands, everybody's favorite command lately has actually been this one. Let's see. Which means that go and update OpenSSL everywhere, please. We've had a Twitter storm of people coming and saying, so my boss came up to me and said, Heartbleed, we're all going to die. And I said, no, that's taken care of. But we've got 8,000 servers. No, it took like 2 minutes. I ran a Salt command, they all updated, ran another Salt command that like restarted Apache and crap, and we're done. So it makes those sorts of things very, very easy. Now the next level of Salt is all about layers. I might have to ask somebody I know to go find a whiteboard marker. Oh, I think Thane left to get one.
No.
Oh, no, you're back there.
I'll find you something.
Oh. Thank you. Wow, I caught it. That doesn't happen. As they used to tell me in my youth while attempting to play sports, apparently my hands are painted on. Or, as would make more sense to this audience, virtual. I generally can't catch things. Okay. Thank you. All right, so the core idea here with this remote execution system is that we've got the master up here, and then we've got n number of minions, and it sends a command out to them. In this case, it sends this pkg.install and the arguments and the target that it's going to hit, sends it out in parallel to all of your minions that you've got attached. and then they all return independently. And so this has been built on top of the ZeroMQ networking system, or library, which is very convenient because ZeroMQ does all of the queuing for you so that you can handle massive parallel requests into a server. And ZeroMQ makes it very convenient to do these sorts of topologies, okay? So you're able to say, I want to publish to everybody who's latched on to this server, and in parallel it goes and publishes. All right. But this is one of the main reasons why Salt is so darn fast. When we send out one of these commands, it's been made to be incredibly small. And so it's really easy for this tiny, tiny packet to get blasted out across multiple systems. And then the minions themselves are intelligent, so they're the ones that do all the interpretation. So that we've got the distributed intelligence factor. And then when they're done with all of their routines, they independently return in an asynchronous fashion back onto a different interface up on the master. And so if we go back and we look at the master and how it works, is that it's got a router process and then a bunch of workers. So if your infrastructure keeps getting bigger, you just tell it to spin up more workers and it says, okay. And then messages come in, and then there's a publish interface in ZeroMQ that everybody listens to. And what the minions do is that they maintain a long-standing open TCP connection. And then when they return, there's an interface on here called the RAET port, which is short for return. And then they asynchronously attach to that and send the data back independently. So this model has worked really well for us. And it makes it, again, very, very fast. But we've run into a number of problems with it. And so the title of the talk, the attempt of the talk is to explain 3 different approaches to the networking that we have inside of SALT. So one of the problems that we run into is, is that when we've got this situation, all of the systems out there have what we call a minion on them. So you've got to go and install an agent on all of your systems. Now some people find that a little on the cumbersome side, or it's restrictive based on what their deployment looks like. And so last year, near the end of last year, we released Salt SSH. Now the ZeroMQ system, which I've just described, it uses this pub/sub thing, long-standing TCP connections that are connected back up into the master, and then all of this asynchronous communication over ports, etc., etc. Now obviously we can't do that sort of fancy stuff with SSH, especially an agentless SSH. You can set an agent up on a system and use SSH as a channel, but that's very different from making something that's agentless. And if we're going to go through the trouble of making a brand new transport system for a giant management platform like Salt, we're going to make it that we're going to make one that gives us a lot of clear advantages. We're not going to waste our time just reinventing the wheel. Okay. It's blue now. Okay. So the idea with Salt SSH is that you've got a single master system here. It's not what an M looks like. Okay. And then lots of target systems that are just listening on SSH. And then Salt SSH does a parallel execution the same way that this system does. But instead, you've got the master up here, and it sends out, and it opens up an SSH channel, and then executes Salt call out here. It's quite slick. What Salt SSH does is that first it SCPs what we call Salt Thin, which is Salt, but all of the networking stuff has been stripped out of it. Okay? Sends it over the wire and unloads it in a subdirectory in temp. And then sends another SSH execution to say, now execute with this little thin thing, And if you want, when we're done executing, go ahead and clean it up or leave it there so next time we execute, we don't have to deploy it, so it's a lot faster. Okay? So the obvious problems here is that we're doing multiple SSH, independent SSH connections that need to happen to send out individual routines. So there's problem one. Subsequent routines, when we've already deployed this salt thin thing, are really fast because it just caches it. So it's all still one routine. But that's still one of the problems that we run into, performance-wise. And then what we do is that up on the master, when we execute salt call, it has a process pool of how many SSH processes or connections are we willing to manage in parallel. And so you can make that pool bigger and smaller. But that means the salt SSH is still really fast. We can communicate and do that test.ping thing I was showing you across 100 systems. And instead of it taking a third of a second, it'll take about 2 or 3 seconds, which for SSH communication, that's really good. But the main difference here is the behavior of how it scales. So now I need to erase something. So the behavior, sorry?
Hands work pretty well.
Hands work pretty well, do they? So I'll figure something out. I'll use a hand or something. Or I'll take a shirt off and use it. Actually, I've got a Tux doll in my bag. Maybe I'll use that. Guru Labs will give me another one. They like me still. Despite my best efforts otherwise. Now, oh, hey, thanks.
Same guy that gave you the marker.
That guy's useful. What's your name, useful guy? Nate? All right.
Oh, hey, Nate. No, a couple of people in this room from past lives.
What the devil was I about to talk about?
Salt.
Okay. Salt? That's all I talk about. My poor children. Okay, so that's right, performance vectors. So if we've got time over here, and we've got minions over here, Salt SSH's performance vector looks like this. Salt's performance vector looks like this.
What was the first one?
Okay, so we've got Salt, classic Salt with ZermQ, and then Salt SSH is much more linear. Okay, and then this will go ahead and scale out to, we'll say about 5,000 systems out here. Okay. Now ZermQ will keep going. We've got our largest single master ZermQ installs out there. Or with a single master are generally around 15,000. Now, most of our large deployments, they use what's called a syndic, so they build tiers. Now, because even if you've got 100,000 machines, it's very rare that you think about them all as a single globular unit. That does happen. Twitter's got a deployment like that, for instance. But it's extremely rare that you don't want to chop those up a little bit, okay? So, great, grand. We've got the ability to do minionless, but it doesn't scale as well as ZermQ. And so, a lot of what we see is that people like to use Salt SSH down in the lower numbers, up to a couple hundred maybe, tops. Usually by the time they're up to 50 or so, they start seeing the benefits of just using Salt with ZermQ. But it is certainly capable of scaling to a certain extent. We've been able to demonstrate it working across many, many hundreds and thousands of systems at a pretty good clip. Okay? Now, the next thing that we run into is this question of performance especially when we get up into these higher numbers. Because as many of you are aware, when you start working with really large numbers of servers, very interesting things begin to happen. Things that you didn't expect. I mean, we're not just talking about, wow, we found a race condition. We got rid of race condition issues in Salt with large numbers of servers back in like the beginning of 2012. That's been sorted. But you just run into very interesting scaling problems. So if we come back and we look at ZeroMQ and look at how it works. What ZeroMQ does is that it is built on top of TCP, and then on top of TCP, okay, it's got POSIX threads.
Below.
On top. Yeah. Stay with me. You look terribly concerned. Okay. Okay, and then on top it's got a queue. And then on top it's got socket types. All right, and then they're all glued together in this single kind of black box. It's not a modular system. We can't go in there and modify how these underlying behaviors are working, and it's very difficult to go in there and manipulate how they're working or even see what they're doing. So what ZeroMQ does is that every time it makes a connection, it keeps this TCP port open and assigns it a thread, a POSIX thread, okay? That means that inside of Salt, every time a minion connects, it needs to allocate a POSIX thread to track said minion. I'm sure that you're able to start to see in your mind that that we might run into some scaling issues here. We've got 10,000 systems and they've all got POSIX threads open that we need to be tracking up on a Salt master. And this is definitely a problem that we run into. The next problem that we run into is that the queue itself is buried below this socket type idea. Now, when I talk about ZeroMQ problems, I need to reiterate the ZeroMQ is incredibly awesome and incredibly fast and incredibly good at what it does. I certainly don't want to come across as bashing ZeroMQ. I'm just trying to illustrate that when we deal with certain levels of networking problems and networking situations, that we need to start thinking beyond its capabilities. Okay, so we get a single thread, and the way Salt's architected, we actually have to allocate 2 threads for every minion. Okay, and so we're the pthreads layer. ZeroMQ is an asynchronous protocol, but it's built on top of TCP, so it's an asynchronous abstraction built on top of a synchronous network connection. Okay? And so then we get up to the queue layer. How the queuing works is that you send messages, and the messages go onto the queue, and then they're popped off of the queue. And it's a queue. It's not exactly the most complicated realm of computer science. But the problem is that queue is directly associated with the socket and the type of socket. So its behavior cannot be manipulated. We cannot build priority filters into the queue. And the behavior of what that queue does is very static. And then we've got the concept of socket types. And so the idea of socket types in ZeroMQ is that you can build a socket that's a published socket and a subscribed socket, so that you've got this high-level, conveniently put together behavior for you. This is a great thing. I mean, we've been able to make great strides using this model. But the problem that we've run into is a couple of problems. One is that when you get up to larger scale, these things do start to break down. 2, we want to be able to manipulate things like the socket type more. We want to be able to manipulate the queue more. We don't want to be creating pthreads And we don't necessarily want to be using TCP because of a lot of other inherent problems. I mean, we wouldn't need the P threads if we're doing UDP. Because instead of tracking all of these connections, instead of tracking all these connections by the maintenance of a TCP connection, we'd be able to track these connections by just variables. To say, I know that there's a guy out there until he stops pinging me, kind of thing. All right. And so this is where our next system comes into place, which is a new piece in SALT called RAET. Now, the idea behind RAET is to have a more flexible networking system. And so if we continue this chart out, SALT, the SSH approach has long become untenable. And then the 0MQ approach, we get out here to 10,000, and it's still tenable, it still works, but we start to see some hiccups out here because, that's kind of what you see at the 10,000 mark anyway. And then there's a real question, and then to get it beyond this, we've got to start building tiers. But what we've seen with the RAET system is that it follows roughly the same line as SALT 0MQ. I know I don't have like a ruler here, but it doesn't. But we're not running into the same hiccups over here. All right. And so yeah, this one just kind of breaks down after 15,000 or so. And we've got to really stretch it to get it there. We start to see hiccups with 0MQ and SALT between 8,000 and 10,000, depending on what people are using it for. So when we look at some of the biggest SALT deployments out there, like LinkedIn, they've got 30,000 systems. Some large companies that don't let me tell you their names, I hate those guys, have well over 100,000. But they start to see those things break down. Okay. All right, and so what happened is that we had a bunch of companies come to us and say, hey, we'd really like it if you guys are real smart dudes, if you can come up with something that could allow us to scale even more. And so one of these companies in particular came and said that they didn't like 0MQ at all because it's licensed under LGPL 3, and we've discovered many companies won't touch LGPL 3 or GPL 3 or anything with a 3 in it and a license. They're just horrified. And that was one of our primary motivations, because they came and they paid us a lot of money and said, you've got this design thing for RAET, and we want to make that happen, and as long as you don't license it under LGPL 3. So we were highly motivated to do this. We've had a few people criticize us and say, why would you bother? SALT works really well as it is. Why bother trying to make something that goes beyond these scaling points that only apply to a subset? But there are many, many, many reasons, a lot of motivations to do so. Now, the difference with RAET is that, so we've got 0MQ, and then the difference with RAET is we base it on UDP, and then we've got a UDP protocol out here that takes care of reliability, ordering, all those things that TCP does. But we've built a protocol that keeps it truly asynchronous on the wire. All right? I've already lost someone. That's embarrassing. Okay. So we're able to keep it truly asynchronous on the wire. And that also means that we don't have compound overhead associated with more and more systems that are checking in. We've just got a small amount of data that we have to add onto the pile for tracking those systems inside of memory, which is a lot more sustainable. All right. And then one of the other problems with 0MQ is that when we started using it, it didn't have any cryptography inside the stack. So we had to build cryptography on top of 0MQ, which is very difficult. And then when they did introduce cryptography in the stack, it was built in such a way that it could not do in-band key distribution, which made it unusable on large scales. So we're still yelling at them about that. Okay. Although admittedly, they've done a very good job otherwise. I mean, don't get me wrong. I love those guys. We're not throwing away ZeroMQ. We love ZeroMQ. All right. But we're able to build the cryptography directly inside of RAET and build it in such a way that's extremely flexible, usable, and fast. And it's using Dan Bernstein's elliptic curve, the 255. I totally just forgot the number. Anyway, Dan Bernstein's curve key algorithms, which are incredibly fast, elliptic curve algorithms, and also many good things have been and are being said about them as they're continually deployed. We're talking to one of the world's largest security companies because they're in the middle of a customer engagement and a deployment with us. So just list off in your minds the big security companies out there, and it's one of those. Again, don't let me tell, we got to build this crap into contracts and everything with these big guys. You can't say who we are yet. But they asked us, they were really excited about RAET, and they said, how'd you do the cryptography? And when I said, I used Dan Bernstein's curve CP algorithm using his elliptic curve keys, and so it just follows his spec to a T. And they said, oh, good, because he's the only one we trust right now in cryptography. All right. So what we start to see here is that you'll say, oh, and there's presence. That's really important. And you say, but there's things missing. There's no queue management, there's no socket types, there's no concept of a pub sub built into it. You can't use this. This is not okay. But so this is all abstracted as a truly asynchronous fundamental protocol, which means that it's extremely easy to build our own socket types. So the pub sub system that we build on top of RAET is literally completely doable inside of a for loop, and it's faster than ZeroMQ. So we don't need to be bound into specific socket types. We can build whatever we want. And so one of the other problems apart from just scale that we run into with ZeroMQ is that it's very difficult to build ad hoc topologies of systems where you've got a lot of truly distributed peer-to-peer communication capabilities, all that kind of cool stuff, which again particularly shows itself as an issue when we're dealing with scale. But now we can build those topologies directly on top of RAET. It stands for the Reliable Asynchronous Event Transport. And there are a few other UDP protocols that are out there that are open source, but there aren't any which are message-based. They're all stream-based. And there aren't any that have usable built-in cryptography and are completely separated from something else. So for instance, inside of new versions of Chrome, the Google guys have built a streaming UDP protocol, but it's directly coupled with Chrome. So you can't take it out. All right. So, what?
Would it be possible to implement RAET on top of what they did in Chrome? Or just nothing?
On top of what they did in Chrome? Well, yeah, if we re-implemented everything they did in Chrome outside of it, and we basically followed their model, and then it wouldn't fit our needs because it would be a streaming protocol instead of a message protocol. So, yes, but it wouldn't work for us. Okay. Now, the other thing I should mention about RAET is that RAET has been designed by one of our engineers who was involved and has been involved in designing UDP protocols for government and industry for the past 25 years. It's a guy who's designed something like 5 or 6 UDP protocols before. He knows his stuff, which is why it works. and he knows the corner cases. He knows where the bodies are buried. It's been very beneficial to have Sam Smith with us. I got to throw a doctor in front of that too. He's got a PhD. He's a smart dude. Okay. All right. Let's see. So my next question is, I've given you an overview. So my question for you guys, I've given you an overview at this point of the different scale vectors, the motivations and the reasons for why we've got multiple transport systems, the problems that we're working on solving, and what vectors and what scope these problems fall into. So my question is, I've got another half hour. We've got some more experienced salt guys in here. We've got some less experienced salt guys in here. Who would rather that I go on a track and talk about how to do like config management and talk about the event system or maybe inside of Salt? And who would want me to go and talk about the depths of how more of these networking protocols work?
The networking protocols.
So who wants the protocols? Okay. I'm really sorry, the four of you. All right. So, we come in here and we start looking at RAET. Now, RAET's architecture, I've only talked about it with respect to the UDP system. But so we know what UDP is. We're all adults. We know what building a protocol on top of UDP is. I've gone over the cryptography. Let me talk about presence really quickly. Presence is something that we are halfway through implementing right now. So this is more or less how far up the stack we are on the RAET deployment. Now, RAET itself has been built entirely into Salt. So you can start up Salt, install the RAET dependencies instead of the ZeroMQ dependencies, and then you change one line in the config files to say transport RAET, and everything works as it normally works. Okay? All the Salt commands work, they look the same, they work the same, etc. Okay? But all right, presence. Another one of the problems, and one of the central problems, especially for those of you who've used Salt, you may have noticed that you send a command out, and then the command line kind of waits for a few seconds before it finishes. Now, the reason that Salt does this is that on ZeroMQ, we send out this pub to all systems, and we don't know who's going to return until they return, because they all return asynchronously. We don't have a finite list of expectation relative to who's going to talk back. We just can't get that data out of ZeroMQ. And it's been really the biggest thorn, the most aggravating thing to me personally on the development of Salt. But so with RAET, we've got this concept of presence. The concept of presence means that the protocol layer itself is tracking who is truly attached to you at all times. Which means that when you send something out, you have a very finite view of who is out there, who's going to get it, who's going to give it back to you, so that we're able to build tracking systems that glue together the caveats that we run into in asynchronous deployments. So gluing these things together is what makes it easy for us to be able to have, again, a perfectly finite view of who is going to respond. Okay? That's really what presence is. Now, we built the presence system on top of ZeroMQ. Yes?
Do you guys have timeouts for network partitions, or how do you deal with a node going down for a long amount of time?
So inside of RAET, when a node goes down for a long amount of time, it gets flagged as down inside of the other connection. I'll talk a little bit about how the actual connections in RAET work here in a second. But yeah, once it's gone for a period of a reasonable window of time, it's flagged as gone. And so we just don't bother shooting worthless packets over the ether at it. Okay. That's right. Okay, thanks. Sorry, I'm kind of a scatterbrain. So, Actually, and yeah, that's basically the last piece of presence, is that if something's gone, it's exposed. The other main idea of RAET is that all of these layers are exposed. The cryptography, for instance, has a simple, straightforward hook that allows you to write a class that just implements an interface. You pass it into RAET, and then that class will do all of the key management that you need to maintain the cryptographic system for you. Okay? All right. Now let's see. If we start to look at how RAET actually works, we've only talked about it in the sense of UDP. So we've got a host here and a host here, or actually they're hosts but in RAET vernacular, which you never need to deal with if you're using Salt, but if you're writing RAET, you'd have to learn the RAET vernacular. We have an estate, okay? And then they communicate over RAET's UDP stack. Now the idea here is that you create a stack object, a UDP stack object in Python. And then you give that stack object some information. You basically say, I've made a stack, and it knows who it is, and it knows where its remote estates are, or you register with it a remote target to go and talk to. Okay? And then, as communication goes back and forth between these two estates in RAET, they just populate these queues which you have full visibility into. They just show up in your code as double-ended queues in Python. So you can just pop off of them. Now, when a message comes into an estate, it ends up on the UDP stack queue. And so then your application out here can pop it off of said queue and deal with it. While you're dealing with it, there's a micro-thread system down here inside of RAET. So they're micro-threads, so they're running in one thread of execution, but they're properly separated. And this micro-thread system down here inside of RAET is still able to pop messages off and populate queues. Okay? So then you're able to handle it. Now when you handle it, you can either do it inside this process here and shoot it back, a very static, old school way of writing code, network code, or we're able to extend into the next thing that RAET's able to do, and that is to create what are called yards. Now this idea has to do with the fact that RAET comes with a Unix domain socket stack as well. And we're in the process of building out stacks that behave in a similar way to a Unix domain stack but work on Windows. We're also admittedly in the process of building a TCP stack so that we can do very specific types of network traversals more reliably. Now, the yard here can be another process. Now I mentioned before, on something that I've already erased, that when you start up the Salt master, it spins up all of these worker processes. Okay? Because as many of you who here knows Python, how well does the threading library in Python work across multiple processors? Yeah, that's kind of a problem. Okay, what?
More or less not at all.
Okay. So in Salt, we spin up lots of processes to handle the work, and so it's distributed across these processes. But the nice thing about RAET is that its addressing scheme is able to track processes that are communicating. So if I've got a yard on that end and a yard on that end, they've got IDs, and so this guy can make a message, send it to the estate sends it down here, and that estate routes it to its yard, and then it can go back along the same channels. Now the convenient thing about that is that we are now able to, in a very seamless, secure, and very, very fast way, have a process up here continually communicate with a dedicated process on the other side. So basically it's inter-process communication over a network that is seamless and asynchronous and fully encrypted. Okay? Yes?
This might be related, but does that mean that presence also includes like presence of services?
It can, yes. It doesn't yet.
Okay.
But yes, that's
the second half.
That's definitely on the list. I mean, if we want to look at the phases of RAET development at this point, so we're working on presence right now. RAET's fairly young. I mean, we've only got the test system going in it. So the full unit test and integration test suite that we've built into RAET has been running for like 4 days now. It stands up to it though, which is good. We beat the ever-loving tar out of it with every commit. And you can go see those on our new Jenkins server that we haven't made live yet, that's at cookingwithsalt.org until we retire the old one at jenkins.saltstack.com. Let's see. So now we're currently working on presence. And then some of the things that we're working on after presence has to do with the attachment of external resource tracking. So like you're saying. It also has to do with the use of a function of the elliptic curve keys in the cryptography that allow us to create group keys, which is very similar to how bank cryptography works, that will allow us to do things like, so one of the problems that we have right now is SALT. Everyone gets this. This is hopefully a straightforward graph.
Has a bit of a slope, but
yeah. But so one of the problems that we run into with SALT is that we've got a number of techniques to make the SALT master redundant. So that you can have multiple SALT masters. So SALT's multi-master system means that, say you've got 3 masters, and then each minion just maintains TCP connections in parallel to all masters. Obviously there's a limit to this. So that's one of the failover techniques. And then another failover technique that we're introducing in the Helium release of SALT coming up in the next month or so is DNS-based failover of the SALT master. But none of those failover techniques share data between the masters because of the restriction on building cryptography out on top of ZeroMQ. So one of the main things that we're looking at again with RAET is the ability to build in this group key concept. We're not even sure we can do this one yet, by the way. It's on the roadmap for further investigation. Everything we've seen thus far says that we can. So, but don't bet the farm on this one. But the idea there being is that we'd be able to create separate authenticated encryption groups so that we've got an underlying layer that ensures security between peers of hosts. And again, that idea is also along the lines of not only that masters would be able to communicate with each other, but also the minions would be able to securely cross-communicate without having to initiate handshakes with each other, but be able to cross-communicate with only initiating a single handshake with their top-level master system. Because as soon as you have to do reliability of cross-reliability of handshakes across peers, then you run into one of the principal problems of SSH that the creators of SSH are currently yelling and screaming about, which is the fact that you have distributed authentication of users and resources, which means that it cannot be reliably tracked. This is one of the main reasons, and I should have said this earlier when I started talking about SSH. One of the things to keep in mind is a lot of people come and they go, Salt SSH, that sounds great. It's agentless, and it's still really fast, and I get most of the capabilities of SALT, very few things it can't do that SALT ZeroMQ can do. And some people come back and they say, SSH is more secure than, it's SSH. But the reality is that the creators of SSH have been on a tirade for the past 5 or 6 years telling everybody to please don't automate over SSH. Because we go back and we look at a lot of the security breaches that have happened. A lot of them happened because of SSH issues. Because it's really easy for one person to leak a key. If you're using Salt SSH, you've got, say, your laptop, which connecting to all of your servers, telling them what to do, which is in and of itself reckless. Right. But if somebody loses the private key on their laptop, it's all over. And SSH is designed that humans handle keys. And humans are one of the most insecure facets of any security system.
Insecure or unsecure?
Oh, whatever.
Both.
Both, yes.
Now, Salt's key system is made so that humans never have to touch the keys. And you've only got the private key that's controlling your minions up on the master in one place. And if that key did get compromised, even though we've lowered the social vectors for that key to be compromised, if it did get compromised, the minions themselves aren't binding to a port in the 0MQ model, which means that you can't directly attack them. You can't reach out to them with the private key you've compromised. You would have to also compromise the network and convince them all to connect to you instead of the master. And by default, we've got routines in there that prevent them from doing DNS hops. So you couldn't do like DNS spoofing to pull it off either. So again, keep in mind if you use an SSH system for automation that there's some very legitimate security concerns to be aware of. Okay.
Are you performing those checks on a hardware-based level, or you're actually looking at the MACs that are exchanged during the primary key exchange, or you going up the stack a little bit more to the IP address?
Yeah, it's primarily IP address tracking. Yes.
I was just curious to know.
Yeah, we've got some ideas with RAET how we're going to build in MAC address tracking, but then there's. We could talk about that for like 4 hours. Okay. All right, so let's see, where are we at? I'm actually out of time. So there's a ton of other things that I could talk about. But that's the basic idea. RAET is separated into the concept of estates and yards. It comes with all of the domain socket components in it. It comes with addressing schemes that allow you to do some pretty cool stuff with respect to tracking messages. And a lot of the reasons why it's able to do these different things is because it was built to solve the problems that Salt is solving, which means that it already had a kind of a high list of things that it had to pull off. And then we had the benefit and the extreme luxury of being able to create a backbone system when we're already a little over 3 years into a project, and we've got a lot of visibility into what actually should be happening over the wire. I mean, it's been a fantastic experience to sit down and say, this is what we've learned, and we know how to apply it, and these are the things that we've learned relative to massive scale deployments that very few people have the luxury of being exposed to, whereas we get to work with guys with 10,000 plus deployments every day. So we see it over and over and over and over again. So we have a very unique experience set, a very unique view, and a very unique opportunity when it comes to building next generation scalability systems. All right. Any questions, comments?
I have about 5 million questions.
Okay, so it sounds like we'll have like a powwow in the hall after this for 3 hours, one of those. Okay.
Unless it's documented on your site, I'll just go read it there.
Yeah, that's the thing. It isn't yet. Most of this RAET stuff it's documented, but it's very lightly documented. Once we get presence in, we're going to take a side and spend a great deal of time coming through and building out a lot of white papers around it, explanation of the underlying topology, make sure that the entire behavior of the cryptography stack is documented, which is easy, that's already documented. We follow the curve CP spec put out by Dan Bernstein to a T, and just add the ability on top of it, which we do need to document, which is in-band key exchange, which follows all the recommendations for in-band public key exchange.
You're signing all that, all your payloads?
Oh yeah. All the payloads are signed. All the payloads are signed. All the headers are signed. Headers by default are in the clear so that we can route. But we don't put any additional information in the headers, which isn't already available, which isn't defined to be a headerable in Dan Bernstein's spec.
You're not wrapping all of this in SSL at all?
Right. There's no SSL. All of this uses Dan Bernstein's cryptography. It all uses libsodium.
That's NACL then?
Yeah, it's NACL. Or SALT. Uses SALT cryptography for SALT.
So does that put that initial payload back at risk for interception?
No. It follows all the specifications of normal initial key exchange that are adhered to, that are specified by Diffie-Hellman, and that are adhered to by SSH.
And that stuff is such cool math.
It is very cool math. All right, I'm clearly getting kicked out. Thank you.
Thank you.
Who is it that I should chat?